We're going to look at bonds one at a time, starting with carbon-carbon bonds. And of course, nearly all organic molecules contain carbon-carbon bonds. The exception would be something like carbon tetrachloride doesn't have any of this, but pretty much nearly all of them have a carbon-carbon single bond. And so that's why that absorption, even though you'll find it in an infrared spectrum, really doesn't matter that much. It's not very useful because everything has it. On the other hand, not all compounds have a CC double bond, so those are very important. So you can look for that stretching frequency at about 1660 inverse centimeters, and the triple bond stretching wave number is about 2200. Very distinctive, a CC triple bond. I'm going to go ahead and start this animation here. So what we're looking at is the stretching of a single bond, two single bonds, and I'm going to switch to double bond at about 1700. You must take these Gaussian results, this program, with a grain of salt. They're often a little bit off from what reality is. And now finally the triple bond stretching, that's 2200 or so. Okay, so triple bond, double bond, single bond. Again, the single bond stretching, not very useful. Double bond is somewhat useful, and the triple bond is very distinctive in an infrared spectrum, but that's what's going on. Okay. Do you have to know these numbers? Kind of. The triple bond is very distinctive. Nothing else really shows up at this wave number, trust me. And so that one I want you to be familiar with. Also the CC double bond, yeah, that one's pretty distinctive. You can know that one, but this one's totally useless for us. Everything has this one. Okay, so let's move on and talk about carbon-hydrogen stretching. So we just left carbon-carbon stretching. Now let's look at carbon-hydrogen stretching. And once again, when it comes to a single bond, CC single bond, and then single bond CH, this is not a very useful thing to look for in a spectrum because every organic molecule, practically speaking, has this, and so not too useful. On the other hand, yeah, you can sometimes spot this one. So this is the CH bond that we're looking for, and this carbon is part of a double bond. We're looking for that absorption at 3000 and 3100. And then finally a terminal triple bond, the CH bond, we're looking at 3300. This one's pretty easy to spot. Now, why is it that this is the lowest wave number, middle, and highest wave number? These frequencies where we see absorptions are proportional to the strength of the bond. So what it also means is that with 3300, that means that this bond is the strongest, so to speak, and this one's the weakest. And it relates to, once again, this is something that pops up. It rears its ugly head from time to time. The greater the percent S character of the hybrid orbital, and in this case, this is a sp3 hybridized carbon, that's what we assume. The percent S character of this hybrid, sp3, is only 25%. And remember, S atomic orbitals are lower in energy than p orbitals, so the more percent S character, the stronger that bond's going to be. So this one's the weakest. This CH bond right here, the percent S character is only about 33%. And then finally, the percent S character for sp hybrids is 50%, making this the strongest bond. And so hence, this absorption is the highest wave number value because it's the strongest bond. Okay, and this is the weakest bond. All right, so let's move on to an actual example of a molecule. This is a terminal triple bond, of course, and we can look for this carbon-carbon triple bond, but we can also look for this carbon H bond, and the carbon, of course, is a part of a triple bond. So let's label these things in our spectrum. So right away, this is very distinctive, this one right here. This is due to the carbon-carbon triple bond, and that's a stretching absorption right there. Very distinctive, not hard to miss. Okay? The other one that I want to point out is this one. So that's due to not quite the triple bond itself, but it's the CH bond. So this, sorry, I'm writing at an angle, that's why my arrows look really off. But it's this CH bond, and it's to the carbon that's part of the triple bond, so that's that absorption right here, very distinctive. Now this absorption here, everything, and I mean everything, has this, that has a CH bond, so this is due to all these CH bonds that we have in the molecule. Okay, all these things, there's CH2 here, CH2, CH3. Really, there's nothing useful here because every molecule, practically speaking, has this. This is the fingerprint region down here, of course, not so useful except to identify molecules, prove that they are what we say they are, match them up to databases. Really not a whole lot going on here either. So these are the most distinctive. So this one and this one, that's about it for this. Okay, so I managed to find this molecule in a database as well. This is an actual spectrum of this molecule, but this time we have a triple bond and a double bond. We're going to go ahead and label these things. So once again, here's the triple bond, the carbon-carbon triple bond. And what else can we spot in this? It looks like this is probably right here, the double bond. And then this one right here is not quite the double bond itself. It's carbon-carbon, and specifically this bond right here, the CH bond. And then this one's similar to the previous example. This is C triple bond C. It's this bond right here. Okay, so that's stretching for that. Stretching, stretching, stretching. These are the distinctive ones. Once again, this absorption, every organic molecule has this, not so useful in our analysis. And of course, this region down here is the fingerprint region. Okay, so this is a molecule that contains all the above. It contains single bonds, it contains double bonds, well, a double bond and a triple bond, and we can spot these pretty easily in the infrared spectrum. Let's look at OH and CO stretching. So again, molecules, alcohols in particular, contain these types of bonds. And so an OH stretch, this is impossible to miss. I mean, it's one of the strongest absorptions you'll see in an infrared spectrum. Look for a very broad absorption, somewhere between 3400 and 3650 wave numbers. And the CO bond, that one's much harder to find. In fact, personally, I rarely go looking for that bond, but you can usually find it between 1050 and 1150. And here's a molecule. This is methanol, so let me just show you this animation now. So this animation, you're going to see two bonds. So this is this bond right here that's doing a stretching motion, so CO bond. What else can we show you? Let's see what else I'm going to do. I have a feeling I'm going to show the OH stretch as well. Let's just give it a second or two. Okay, there it is. There's the OH stretch. That's a very broad absorption, very strong. Even though it's misleading looking at this graph down here, really, truth be told, in reality, that's a very strong absorption. You can't miss that, okay? All right, so let's take a look at least one actual spectrum. Let me advance this slide and let's take a look. So here's a molecule. Let me just double check. Oops. Let me just double check that that's the first molecule. Yeah, it is. Okay. All right, so this example is a chiral molecule, but that doesn't really matter too much. The fact of the matter is that we have a CO bond and an OH. So right away, the first thing that jumps out at us is this very broad absorption, and that's due to the OH. Specifically, it's this bond right here. It's this single bond between the oxygen and the hydrogen. And I forget already, I think the CO bond is going to be somewhere down in here. In fact, I couldn't tell you exactly which of these three is due to that CO bond, and that's why I rarely go looking for it, because it's usually buried within a sea of other absorptions. So, but somewhere down here, you can find this CO stretch. This one is the obvious one. Now, this is the one that tells us right away that this molecule, if it's truly an unknown molecule, it tells us very quickly that it's an alcohol, and you've got that much in your molecule. Okay, so I'm not sure if I have another example of this. I forget, but let's take a look. So I'm going to advance. I didn't have another example, but that's fine because OH is so easy to spot. All right, so let's take a look at NH and CN. These bonds have a lot in common with the previous, the OH and the CO. The NH stretch is fairly distinctive, not quite as broad as the alcohol stretch, but it's in general, it's in the same region, 3,300 to 3,500. And the interesting thing about this absorption, not quite as strong as the OH bond, but depending on how many hydrogens are attached to the nitrogen, if there's two hydrogens attached, you see kind of two horns on that absorption. If there's only one NH attached, you see one horn. So amines with two hydrogens, just like I said, two peaks, and with one hydrogen, one peak. I'll show you an example of a two-peak amine. The CN stretch is typically between 1030 and 1230. Again, once again, I never look for it. I rarely look for that one. It's usually buried. It's hard to find. All right, let's see what we can find in terms of an example. This is my example that I dug up out of a database. And this is the important one right here. Notice that it has two horns. So here's one horn, here's another horn. And that's the situation where I have a nitrogen with two hydrogens attached. So very distinctive. And down here is probably our CN stretch here. Okay, but other than that, this is what we're looking for. Maybe you're wondering, what if I have a molecule that has both a nitrogen H bond and I have an OH bond? I'm guessing what's going to happen is the OH absorption is going to totally blow out or mask the NH stretching. We try to give examples of molecules and try to work with molecules that are fairly uncomplicated, that only have one functional group. As soon as I get multiple functional groups in a molecule, it becomes hard to interpret this IR spectrum. Okay, so let's look at the carbonyl stretch. This is the second most important, maybe in a tie with the OH stretch. So here's the carbonyl. Just as a reminder, a carbonyl is this bond right here. It's a carbon double bond oxygen. Carbonyl is not a functional group. It's just referring to this carbon double bond oxygen. So lots of functional groups contain a carbon double bond oxygen. This is one of the most important absorptions to look for in an IR spectrum. It's pretty much the first absorption that I always look for, and it's very distinctive. It's usually right around 1700. Very strong absorption, nearly 100% T, excuse me, not 100% T, 0% T, almost 0% T, and typically between 1670 and 1780. Aldehydes are a little bit different than ketones, although it's kind of hard to distinguish these two sometimes. One of the very first experiments coming up is you'll get a chance to oxidize a molecule, but we're not quite sure whether it produces an aldehyde or a ketone. And just by looking at these absorptions where they're found, you're going to be able to hopefully tell whether it's a ketone or an aldehyde. It's sometimes tough to do. Also, what affects this absorption is the amount of conjugation. So if this carbonyl, this C double bond oxygen, has, say, something like this, let me just scroll this in, has a double bond that's adjacent to this C double bond oxygen, that can have an effect on the conjugation, that can have an effect on the absorption value too. So anyways, we'll just kind of ignore that for now. So I'm going to start this animation right away. I jump to the 1700 absorption, and that's due to this stretching of this carbon double bond oxygen. So that's going to be a very obvious absorption. But also with aldehydes, you might want to consider looking for this one as well, because ketones don't have this. That's the stretching frequency for this CH bond that's attached to a carbonyl. Okay, so ketones don't have that same one, and that's another way we can distinguish ketones from aldehydes. Okay, so lots of things can affect this absorption. You got to be careful. Here's an actual spectrum. So this is a ketone, and of course, this is what we're looking for. This is the first thing that jumps out, and this is the C double bond oxygen. So right around 1700, can't miss it. Very strong absorption, nearly 0% T, and that's due to this central ketone. Okay, really don't need to point out too much else. I always say this, but this is present in nearly all organic molecules, so it's really not that interesting. And of course, this is the fingerprint region right here. Okay, this is the only one of significance for us. I've got several examples of carbonyls. So this is an aldehyde this time. The reason why there's a sulfur in here is because it's the only spectrum that I could find that was of an aldehyde. I found these ones at aldrich.com, but it was really hard to find just aldehydes that are pretty simple. So this is what we have. Now, first and foremost, this is the 1700 absorption that we're looking for. So this is the carbonyl. But also aldehydes, a difference from ketones is this little absorption right here. This is due to the CH bond in this molecule right here. So specifically this one. Ketones don't have this, so you're not going to see this for a ketone-containing molecule. And another interesting little feature of this spectrum is this little peak right here. This is called an overtone. And you always find this little overtone as double the value of what this value is. So if you consider this to be about 1705 or whatever it is, 1710, this overtone value is going to be roughly double what this is. It has to do with physics and whatnot, but that's going to be present in this spectrum. Okay, so this is an aldehyde. This is an aldehyde molecule. I may have another one. Let's check. I do have another one. This is a conjugated aldehyde this time, and the conjugation means that this double bond, so this is a carbon, double bond oxygen, and then one bond away, there's another double bond that's called a conjugated system, where these are adjacent to one another. It's double bond, single bond, double bond. That can have an effect on the exact value of this absorption as well. This is definitely the carbonyl that we're looking at, and the fact that it's conjugated makes it shift over slightly in the spectrum. I'm taking a wild guess, but I think this is also the overtone right here, although it's a little bit tinier than the previous example. Okay. All right, so conjugation also affects the value. So aromatic compounds for us, for now, since we haven't talked about aromatic compounds officially, they're compounds that contain a benzene ring, although it's a little more, the truth is it's a little more generic than that, but we'll just focus on benzene. And you can sometimes figure out the substitution patterns of benzene. Substitution means that here's the benzene and replace any of the hydrogens normally attached to benzene with some other group like chlorine or bromine or OH or whatever you want. This one's called a monosubstituted benzene because we've just simply replaced one of the hydrogens with something else. This could be bromine, whatever. And in the IR spectrum, if you look closely enough between 800 and 700, you'll find a pretty strong absorption. The S means strong here at about 750, but also here at 700, and that's what you look for in this region. Orthosubstitution means that you're only seeing a single strong absorption at about 750. You don't have this one. Metasubstitution, you've got a medium absorption, strong, and strong at these values. Para, only a strong one here. 1, 2, 3, substituted, medium, strong. 1, 2, 3. Oh boy, that's got to be a mistake. I think this is the 1, 2, 3. This one's supposed to, that's a typo right here. 1, 2, 4 substitution is this pattern. I never noticed this typo until now. 1, 2, 4. 1, 2, 3 for this one, and this is another typo. I think when I made this figure, I made it with Illustrator. I forgot to update the numbers here. This one's 1, 3, 5. 1, 3, 5. This is also a typo. So let me just fix those right now so you don't have to stare at wrong values. So 1, 2, 4, and this one is 1, 3, 5. But anyways, in the IR spectrum, you can expect a strong absorption here, medium here, strong, medium, etc., etc. So that's if you're looking carefully at these substituted aromatic compounds, benzene rings. Just to remind you, the terminology ortho refers to 1, 3 substitution, meta 1, 4, excuse me, para is 1, 4, meta is 1, 3, and ortho is 1, 2. So here's an actual spectrum of bromobenzene. Let me just sketch this out so you can see this. Bromobenzene is a benzene ring. That's the worst benzene. It's really hard to draw at an angle like this on my little sketch pad, but this is considered monosubstituted because we've only replaced one of the hydrogens with a bromine. And if we back up, let me just double check this because I don't remember these half the time myself, but I'm going to back up monosubstitution. Back up. Monosubstitution, we should see a strong absorption 750 and one strong absorption about 700. Let's see if that's true. So here's our strong one at about 750, and here's the strong one at about 700 or so. So yeah, definitely. So the monosubstituted, we see those two peaks that we expected to see. Now this region right here, I didn't talk about this yet, but this region is over yonder in this side. Sometimes you can actually figure out that it's monosubstituted too based on the pattern that you see here. This is just a zoomed in view of this. These pictures, what you're looking for, I didn't put it into the slides here, but if you search the Pavia textbook in the infrared spectroscopy section, they'll show you the pictures of what these things look like in this region rather than looking down in this region. But you'll see these. They're really hard to spot sometimes, especially if you don't have a clean spectrum. These ones are usually a little bit more obvious down here. All right, so this is called metaxylene. Metaxylene. Let me show you the structure of this one now. I'm going to face forward so I can get this as a decently drawn structure. So benzene. Xylene is, here's xylene. So xylene has a CH3 and it's meta-substituted, which means that the next CH3 is 2 carbons over. And so this is considered a 1,3 disubstituted compound. And I don't remember exactly, but I have a feeling that what we're looking for is this absorption, So let's double check that one now. 1,3 meta. Let's double check the values, what this should be. Okay, so 1,3 meta, we have strong, strong, And then medium, I forgot to look for the medium, but it's about 890 or so. So let's check that. 890 or so. That would be this one right here. Okay, medium. Oh, you know what? I didn't go. Apologies. that's the spectrum. Sorry. This is what we're looking for. So medium, strong, and strong, and we found them all. Okay, so just like the previous example I was showing you, you can sometimes figure this out as well with this part of the IR spectrum. Again, search Pavia textbook, the lab textbook, and you might see these pictures right here. But definitely these are characteristic. All right, so I'm just going to cut to the chase on the next couple of compounds. So, well, I'm having all kinds of problems. I'm going the wrong direction. Here's orthoxylene. Orthoxylene is pretty much the same thing as meta, except the substitution is a little bit different. So ortho means 1, 2 substituted. And I have a feeling this is going to definitely be part of the analysis. But of course, this region can sometimes be helpful as well. So ortho is that compound. And then finally, paraxylene. There's a really strong absorption here. And paraxylene is this structure. Usually with para substitution too, this region becomes really important. It's usually pretty obvious. It always looks like this little pattern right here. Big absorption, relatively small absorption. And that's also characteristic of a para substitution in addition to this. Carboxylic acids are interesting because you've got the carbonyl absorption right here, but you've also got the OH. And notice that OH absorption tends to shift over a little bit to the 3000 range. And that's why if this wasn't a carbonyl next door to this OH, it'd just look like a normal alcohol. But this absorption switches over or shifts over to the CH region. So carboxylic acids always really have this sort of pattern like this. They generally look like this. And same is true for this compound, obviously. And really when it comes to IR analysis, I'm not so much looking at the values as much as I'm looking at the patterns or the shape of these curves. And carboxylic acids jump out at me. They always look like this, a really broad absorption that starts about here and merges into the CH stretching here. And it has this kind of sloping feature right here, really sharp features here, and then it kind of fades off. It also has the carbonyl, got to have that. It's not a carboxylic acid unless you have this absorption too. All right, so this spectrum is of 1-bromobutane, and this was taken on our FTIR. This is the older FT, but nonetheless, it really doesn't matter because our new one would produce the same spectrum. But this is a neat analysis, which means that I took this 1-bromobutane. I believe it's a liquid, and I put it between 2 salt plates. I ran the analysis, and of course, I've got the 4,000 to 500 wave numbers, and I've got the %T here. I'm not entirely sure what my point was here because I had plenty of examples already, but 1-bromobutane, of course, looks like so. Really, in an IR, it's kind of a boring compound. The only thing that we see really is the normal CH stretches, and this bond right here, CBR, I'm sure it's here somewhere in the IR spectrum, but I forgot a long time ago. I don't think I ever knew where this absorption occurs. So really, it's the absence of a C double bond oxygen here. It's the absence of OH. It's the absence of triple bonds. It's really the absence of all these other function groups that we just looked at that tells me that this is some sort of kind of relatively boring compound with not much going on in terms of really obvious stuff. And of course, this is the fingerprint region, so this spectrum is always going to look the same for 1-bromobutane. So that's another way to identify this compound is just by matching up spectra, but not really exciting, but that's 1-bromobutane. Here's another example. Unfortunately, like I said, I wrote all over this thing. I think I used this example as a training exercise when I was teaching people IR in the laboratory. And this compound, let me just sketch this one out. It's helpful to see the structure. So 2-butanone, 1, 2, 3, 4, and the carbonyl is here, and the 3-hydroxy, so 1, 2, 3. So the hydroxy group is going to be here. Keep in mind, too, the name is such that the carbonyl outranks the OH. That's why the OH, the hydroxy, is at the third carbon, and the butanone, the ketone, takes precedence in this name. So here's that carbonyl absorption right here. This is the stretch, and of course we've got a very large alcohol peak as well. So everything that we expect to see is there: carbonyl and OH absorption. Just marching through spectra here, just giving you lots and lots of examples. So let me draw out this structure. This is benzaldehyde. So benzaldehyde starts with a benzene ring. I'm going to put the aldehyde arbitrarily at the top, and then 2-chloro is here. So a couple things we could be looking for. First of all, the most important one is going to be the carbonyl, and we definitely see that, although it's a really strange value here. But carbonyl, here's the absorption. It's this very large absorption here. What else can we find? Benzene is part of this absorption here. If we look carefully enough, we could probably find that 1,2 substitution somewhere down in this region right here, right about there. What else? The aldehyde is going to have this right here. Ketones don't have that. What else can we find? I think that's about it, aside from the CH bonds that are probably these absorptions here. All three of these, or maybe all two of these right here, are the CH bonds in benzaldehyde. So this one's a fairly complicated one to figure out. Oh, by the way, too, this value is way off from 1700. It probably, I'm just going to go out on a limb here and say it has to do with the conjugation of the benzene ring with the carbonyl. I think that was my point about putting this into the notes here. But conjugation with the double bond oxygen really has an effect on what that actual shift value should be. It's also disubstituted benzene, so we can sometimes find some information here, but also definitely down here. Here's a carboxylic acid. And the carboxylic acids generally have this pattern. Let me just show you the structure here too. So benzoic acid, benzene, carboxylic acid, and then 2-chloro is here. We've got the typical C double bond oxygen absorption. Again, it's not very close to 1700. I guess this sort of blows out my theory of conjugation, because this one is actually shifted to the right of 1700. The previous example shifted to the left. I don't have an explanation for that. It's just the way it goes. But, you know, you can't miss this absorption, so it's going to be somewhere in the neighborhood of 1700 for most examples, although there's some pretty serious exceptions to that, as we saw in the previous example. Carboxylic acid looks pretty average here. This broad absorption is going to be due to the OH, and that's pretty classic for a carboxylic acid. And of course, this is the fingerprint region, as always. So I've already gone over this, and in fact, I think I wasn't paying attention when I made the notes here, because this is just a duplicate discussion of what I've already covered. So here's toluene. Toluene structure is, well, it's a monosubstituted benzene ring. And once again, this pattern, you're always going to find this for monosubstituted benzene rings. Very classic, 1, 2, 3, 4. But also we can go looking for this region down here. So with monosubstitution, we expect strong and strong, roughly at 700. And so if I go down here, here's something that's roughly 700. And right next door is this other one right here. So these are the two absorptions here that correspond to these two absorptions here for monosubstituted. Metaxylene, again, I guess I've just duplicated everything I've already done previously, but here we go. Here we go again. It's nice to have this chart right to the side, so it makes it a lot easier to look at these things. So once again, here's metaxylene, CH3, CH3. This is a disubstituted compound, and more specifically, it's 1,3 disubstituted, and we should expect to see this pattern right here. So strong, strong, right about 700. So 1, 2, and then I'm assuming that this is the other absorption that we're looking for, which is, oh boy, I think it's this one right here. Okay, so that's a medium absorption. These are strong absorption, so that makes sense. Paraxylene. We'll just do this one really quickly. Paraxylene. I've already showed you the spectrum of this one, but para means this. This region is pretty obvious. That's pretty classic for para-substituted compounds. But also when we look for this absorption, it's about 800. This one's a little bit less than 800, but it's there. Very strong absorption and pretty easy to spot in the spectrum. Okay, so let's talk about the strengths and weaknesses of IR spectroscopy. I've taken you through the major functional groups and what to look for in an IR spectrum. So that's the analysis or the interpretation of one. It cannot solely be used to determine the structure of an unknown organic compound. So if the compound is totally unknown, you can't just simply take an IR spectrum and expect to figure it out. The only way to figure out the structure is if you have a pre-existing database of known structures and a computer or you manually match up the database structure with the structure that you have. That's the only way to identify. Otherwise, you can't use it alone to determine an unknown compound. Of course, a lot of the signals are ambiguous, so there's, the more atoms that you have in your molecule, the tougher it gets because there becomes a lot of absorptions. It really gets hard to figure out what's going on where. It's used primarily to detect the presence or absence of functional groups, the key word being presence or absence of functional groups. So I can quickly tell whether my molecule contains a carbonyl or it doesn't contain a carbonyl, the presence or absence of that absorption. Every molecule has a completely unique IR spectrum, so the technique can be used by, and our instrument in our lab was donated from the crime lab, so they did this all the time. They had a database installed that contained lots of structures, and they just simply, they used it for arson analysis, and they would just simply match up the spectrum against, I misspoke actually, our mass spectrometer was from the crime lab. Our current IR is brand new, but I would imagine we can install a database. I didn't look, but a database has structures where we can match stuff up to. Using IR spectra, we're going to use this in tandem with NMR spectra and mass spectrometry to identify functional groups, but also figure out structures. So how do we interpret? Well, we just talked about this. Personally, what I do is I rarely look up tables of data and look for actual wave numbers. I just looked at enough spectra with characteristic or very specific functional groups, and I just learned the shapes of these absorptions, roughly where they're at and what the shapes are. For example, OH absorption, very strong, hard to miss. It's always in the same location, roughly speaking. Same goes for carbonyls. I think those two in particular are the two that I look for most. So 1700, and the other one is the OH group. I'm always going to give you the table of data, so if you don't want to memorize shapes or look at lots of spectra, there'll be a table of information related to IR or regarding IR on the test, so you'll have to just look at that for the values, and you're going to always have this. This is the very table that you would normally have on the test. So you can use this if you want to, if it helps you, if you think you like looking at values rather than looking at shapes, then go for it. This is what you want to look at. So this table, I'm always going to provide this to you on the test. You'll always have this. Okay, so now as the last thing we do, let's just look at a couple of sample problems. And so most of these should be pretty easy. Let's take a look and see what kind of damage or what kind of trouble we can get into. The most obvious thing that jumps out at me is this, which is an OH, which means that we can immediately eliminate this one. We can eliminate ether. We can eliminate cyclohexane, this one, and finally this one. The only decision we're going to make is whether it's this one or this one. And the difference between these two is a double bond here, but no double bond here. Typically speaking, double bonds show up, well, there it is right there. They show up right about there. So I'm pretty confident that this is the structure and this one's not, because this structure, which is just has an alcohol, no double bond, would not have this absorption here, but this one does. Okay, so this is the answer. Let me fill in the bubble for you. Okay, so that one was pretty simple. Let's see, what else? Here's another sample problem. So we're looking at another spectrum, and we're asked to figure out which compound this corresponds to. Let's see, nothing is drastically obvious to me right away here, so this might be a tough one. We've got a challenge here. I don't see a double bond, though, so we can probably eliminate all the double bond compounds right away. I don't see an alcohol either, so we can eliminate these two. It's down to an ether or just simply put a cyclohexane. This spectrum looks so boring that I think we're looking at cyclohexane as my best guess as to what this is. I don't see anything that tells me that it's an ether or any of these other compounds. Cyclohexane. Once again, we're going to match up the spectrum to one of the following compounds. So, is there anything distinctive in this spectrum? I don't see a carbonyl. I don't see an alcohol. I don't see a double bond either. Double bonds would normally be here, so I can eliminate this and this. And by process of elimination, I should expect to see a CO bond somewhere, but I'm pretty confident that this is the compound right here. Like I said, you can always look up values if you're not confident about doing this, but I think that's it for the sample problem. So really a lot of these sapling learning problems that you're going to see on Friday are just simply put, here's an IR spectrum, match it up to the compound. What do you think it is? Well, I think that concludes the IR chapter. We've gone through the theory of IR, but now we've looked at the analysis. So after you've looked at a number of spectra, you get quite good at recognizing shapes of these spectra. Remember that alone, IR cannot be used to determine the structure of a compound. So really, it's in tandem with NMR, IR, and mass spectrometry. Those three techniques combined really allows you, it's really powerful combination because it allows you to identify compounds. Okay, so that's it.